So,
technical
problems
partially solved.
So it's a great pleasure to have Maxim presenting us the angular block oscillations and their applications. Thank you.
Okay. Thank you very much for coming after this nice sea swimming. It's perfect. Perfect weather, perfect place. Thanks for organizing, especially Wolf and also steering committee to organize a very excited workshop. And my pleasure is to share with you our last discovery, and especially for community of quantum sensing. And therefore, don't be surprised I changed the title of my talk for like more fundamental physics to more application. And therefore today, my great pleasure to show to you what we mean by angular Bloch oscillation and especially the application for quantum sensing. And therefore, I'm very happy to have brilliant student Bernd with whom we just did this work. And I would like to start to remind, probably it should be very short introduction, what's actually, or a little bit reminder, what's actually Bloch oscillations. It's quite old quantum mechanical effect, which has been discovered by Felix Bloch in 1929. As you can see, that's German Zeitschrift für Physik. It's exactly 1929. He just predicted very neat quantum effect, which you have electron in a periodic potential provided by crystal, and also applied electric fields in order to accelerate this charged particle. And amazingly enough, this is doing great. It was enough to basically just periodic potential, linear potential. You get very specific periodic motion of the particles. And this is periodic motion repeated itself by quantum interference, was exactly as shown by Felix Bloch, just very specific feature, which is nowadays applied everywhere, as we already saw it many times for Bloch oscillation, you know, to accelerate atom in optical lattice and so on, to make it really fundamental breakthrough to quantum sensing. So, of course, this is for electron. It was not so easy to observe it. This is Bloch oscillations. And now you see the first, actually, the try, like more or less convincing observation of this is Bloch oscillation has been done. If you, I'm sorry, this is quite tiny. It's 1992. Especially people modified very specific semiconductor super lattice, because the lattice normally crystal so tiny, and therefore and also electron collide with a crystal so often. Basically, it's just basically lost its coherence, and it was not possible to observe such Bloch oscillation for the original idea of Bloch. But it was possible later for a super lattice. You see, in 92, almost 60 years later. And of course, afterwards, we have this very nice breakthrough done by Christoph Salomon's group, basically in 96. That's exactly Eckhart High. He just exactly gave a talk today. And if you have any questions about how to observe it, Bloch oscillation, but for the atom in optical potential, just might more experimental details, you can ask Eckhart. Exactly. So, and after that, of course, afterwards, it was explosion of the Bloch oscillation physics. You can see this, especially just want to make attention to the paper by Baum and the other book, which is observed even this Bloch oscillation for molecular rotations, which is, you would not even predict it. Where is it? Exactly, it was in the distribution of angular momentum, and it's a function of applied laser pulses. It's periodic function, and it's perfectly follows exactly this prediction of Bloch. And also next, also very nice, but not only electron or matter waves might show or exhibit the Bloch oscillation, but also even the photons. And therefore, there is also photon Bloch oscillations. In a specific, exactly, this is silicon optical superlattices. Basically, actually, it's a photon crystal. So, and of course, it's a more interesting also work for the with all the atoms, especially if you just put in a purity in a strongly which is strongly interacting with an ultra cold gas. You also can even observe Bloch oscillation in the absence of any lattices, which is also interesting. It grew by Nagel. exactly in Austria. So basically, there's a lot of there's a Bloch oscillation, just an experiment with analogous Bloch oscillations. But I would like to come back to original Bloch's idea. Of course, as I already mentioned, basically you have a line, you have a dashboard potential, which is kind of period, and it's a decline with a linear potential. Now we just ask Diego, what is going to be? Can we also just consider this different, a little bit different physical system when we have a ring, but also basically we bend this as periodic potential just on the circle. And the question is, do you have some kind of similar Bloch oscillations? Since now we just call this as a phenomenon of angle Bloch oscillation, because still we will see that will be Bloch oscillation, but now not with respect to the angle, not on the function of x on the line. Now it will be function of phi. Okay. And now my next, I don't know, 40 minutes, I'm going to discuss this exactly what it is angle Bloch oscillation, and most importantly, how we're going to observe. And after this, in the second part of the talk, I will discuss what is good for, especially for the meta waves community, for the quantum sensing, to construct a very compact quantum sensor for the angular acceleration. Because I remind you, oscillations, Bloch oscillation, always induced by linear acceleration. Exactly the same thing here. All this Bloch oscillation with respect to the angle variable will be induced by angular acceleration. And that's what we're going to use it to construct this compact quantum sensor. So let's start it. Sure. First of all, how we're going to basically construct very nice localized meta waves on the ring. For this, we again going to use, sorry, I just moved away. We need to use a very localized, let's say, meta waves on the ring. How we're going to do it? We do it in exactly in this very well-known way. We just make a toroidal trap in order to make this make it let's say trapping with respect to the radial direction and with respect to the z direction, but get it free with respect to the phi direction if I'm using cylindrical coordinates. So this will be done by a toroidal trap, which is exactly with the radius r naught, and that's exactly which is basically painted here by the yellowish color. Now the question is how to create it. Now we trapped it. If it's combined just very strong enough, atoms will be just on the ring. Now the question is how to create it, this periodic modulation of the ring. For this, we use a ring lattice, which will be nothing else than the position of two Laguerre-Gauss beams. And the main feature of this Laguerre-Gauss beams is the following. The first one, for example, is just LGL omega. Basically, it has a very nice plane wave with respect to the phi with the azimuth number L. Okay. The second one, if I just put it parallel and superimpose with minus IL phi minus L, I perfectly just create this condition period because it will be a plane wave in this direction and plane wave in this direction. And of course, this interfere and just get a perfectly standing like wave with respect to the phi angle. Another question is how to create even linear potential. Linear potential, it will be acceleration. Now we have to somehow accelerate this, or like angular accelerating. This is exactly, this is lattice. How we're going to do it? Exactly in a smart, which is just learn it from experimental physics. What we have to do, we have to make a little bit chirp of the second Laguerre-Gauss. And what it's going to be, basically, I just write down dipole, optical dipole potential. It will be constant plus some whatever modulation cosine L phi, like a standing like wave with respect to the phi, minus A, which is nothing else. It's an integral over chirp. And basically, if you just increase certain whatever, like say linear function, integral will give you a quadratic, and a perfect acceleration. Basically, if you follow the maximum, it starts to rotate, because if you just make a derivative of the phase, it will be phi dot proportional to the A dot, which is nothing else. It will be a frequency chirp. Perfect. Now we have all the ingredients, and now we just if it will be trapping very tight, we can exactly just reduce our system to the effectively 1D. Which exactly I have it. Time derivative, one-dimensional, typical rotation with the I is the inertia momentum of inertia. That's exactly amplitude of cosine L phi minus A. And of course, additionally, for the later application, I apply external rotation. And now I have to solve this Schrödinger equation on the finite domain with respect to the phi. So of course, it's much easier to do it, and that's what I'll show to you. That's exactly this is If I just go to the co-moving frame, what's exactly atom experiences? Basically, I just get it only almost like no time dependence periodic potential, optical lattice, but this will be effective rotation rate, which is basically it's a direct sum of external rotation plus the chirp. This is in our heads, and after this one, we're going to measure later. But this is our fundamental equation. We're going to constantly use it. Let me show that exactly this dynamics really will show Bloch oscillation. How are we going to do it? We just firstly just consider angle Bloch oscillation, like mathematical trick. So basically, I just created, for example, like I take this dynamical equation and prepare, first of all, I just prepare the ground state of this potential, only optical. And this is exactly demonstrated on this picture, where the minimum, what's exactly maximum densities corresponds localization of my atom. And you see it's a perfect, this is a periodic modulation. Now, when I create this ground state, I just can slowly start to change this angular acceleration. It's a linear function of time with a sum rate S. Okay. So afterwards, if it will be slow enough rotation, we immediately get this mathematically. We can show this exactly my function given at time t. And this, if I just make it a certain time tb, which is we'll call it Bloch period, it just repeats itself, which is exactly very, very nice phase, which I'm going to discuss it later. And it's an original wave function. After this is certain Bloch period, which will be 2L over S. Perfectly in the similar way on the linear Bloch oscillation, because 1 over rate, that's exactly how you all just proportion to the angular basically acceleration. What's exactly the slope of this potential? Good. Perfect. How we can, so just very shortly, of course, we can also show this result very easily if you just bring the solid state physics formulas. So basically, if my constant, if I have a constant V, I immediately can solve this periodic potential. We know it will be Bloch structure, but now, since I have a phi on the finite domain due to the quantum mechanics, I don't have it continuous bands structure like this up and up. No, it only will be only certain dots. Why? Because angular momentum on the circle or on the ring always quantized. Instead of continuous, I immediately get dots. Okay, so now I just prepare, let's come back to the first step. I just prepare my system in absolute ground state and start to adiabatically slow scan. This is exactly, this is quasi-angular momentum eta. And you see that's exactly, if I adiabatically slow, it's a perfectly adiabatically follow, that's exactly the first band. And you see after 2L over S, because it's linear function, it's a perfectly come back, this state will repeat itself, and so on and so forth. Perfect. Now we did have angular Bloch oscillation. Now the question, what exactly will be our vision about possible experimental verification of this? For that, exactly we do put it like trivial, let's say our theoretical view on this experimental scheme or timeline. So first of all, I just make it toroidal trap, just prepare the ground state. Afterwards, I adiabatically switch it on. This is exactly my modulation with respect to phi, and prepare the ground state in this optical potential, modulated with respect to the phi. And after that certain time, and it's exactly when I finish this preparation, I perfectly start to rotate it slowly. This is by a chirp. I just slowly start to rotate it. This is ring lattice. And immediately just get it. And after that, a certain time, whatever, I just put a time final. I just switched off everything and observed basically angular. I just measured the density, and after from this, I will extract angular momentum. Now the question, we know in the linear potential, let's say on the line, what's the seat our Bloch oscillation? Usually in the velocity. Now the question is exactly an analogous to this linear Bloch oscillation. My periodicity will stay or will be hidden, so to say, or will be imprinted in angular momentum as a function of time, how long I just accelerated this ring lattice. And now if we just calculate it, this is a mean value of angular momentum, it's a function of time, you immediately get this a very nice red line. But you see, this is also guided almost periodic, but it's a little bit guided by the green line. With a green line, it's nothing else, it's my forced, so to say, acceleration. Of course, it's increases my, of course, angular momentum. But if I subtract it, I immediately perfectly just get this periodic motion. That's exactly with the Bloch period, which I mentioned before, 2L/S. That's exactly angular Bloch oscillations. Why it's a periodic? Because it's perfectly just connected basically with the derivative for the energy, Bloch energy. It's a function of quasi-momentum or quasi-angular momentum. Of course, it's periodic function according to the Bloch theorem. That's perfectly exactly the same what we know in the normal linear Bloch oscillations. Great. So we saw it. There is such effect. We also discussed experimental scheme, how we're going to observe, and where we have to look at in order to see it. Another question about application. It's a good, neat, let's say, a very nice phenomenon. Another question of what we're going to do with this. First of all, as I said, first we have to trap our atom on the ring. The question how well we can reduce 3D, quite complicated optical potential with modulation along this phi to the effective 1D system. It's not easy. Of course, theoretically, you can make an harmonic potential, blah, 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 all this. So tons of mathematics. The question is going to work or not. So since we're in a more or less towards the sensing community, my idea will be, let's atom decide and just really to check and calibrate itself. That's exactly how well it's 1D now. What I'm going to do it. So basically the question, can we experimentally find out what's the I and what's the V here? Via performing angular Bloch oscillation or calibrate it. This is our future device. And just find this I and V. Coming from the very complicated 3D optical potential geometry and so on. So how are we going to do it? We're doing the following.